Well, I'm not going to do a long introduction. I think we've got the same people back that we had with us a couple of days ago. So I'll just welcome you all back, and thanks for joining, and thanks again to Professor Iain Woodhouse from Edinburgh University for running these training sessions for us. And a reminder that this is all made possible by the Caroline Herschel Framework Partnership Agreement on Copernicus User Uptake. We're funding this whole suite of projects for JNCC. I'm going to hand over now to Crispin Hambidge from the Environment Agency, who's going to talk to us about how the EA are using Sentinel-1 SAR data for flood mapping and flood response. So thanks very much, Crispin, for agreeing to do this talk, and I'll hand over to you.
Okay, thanks very much, Paula. Hopefully you can all see my screen. And yeah, so yeah, my name's Crispin Hambidge. I'm a senior geomatics analyst at the Environment Agency in the geomatics team, and I've been here for a good almost 20 years, looking at applications for remote sensing for a variety of different purposes, and do a lot of data capture ourselves on our aircraft, including LiDAR imagery capture, which we're currently doing a kind of national program for, but we also do a lot of satellite analysis as well. I just want to give you a little bit of a lowdown on one of the applications that we use the SAR data for. Primarily nowadays we're using Sentinel-1 imagery. One of the really great reasons for that is it's a very consistent data set that's being captured routinely every couple of days or so. But there are a few kind of different applications we use it for. So primarily is flood extent mapping. So that's on kind of two different levels really. One is kind of instant response, rapid response service. So that's for kind of situational awareness during incidents. And then we've also got kind of slower kind of peacetime response service, which is kind of used for things like farmer compensation schemes for when agricultural land gets flooded, and we're sometimes asked to do a more kind of detailed analysis kind of post incident to get a better idea of the amount of land that's been flooded, potentially by kind of holding. And
you should be able to just do the presentation mode. That should still come across on the Zoom.
So yeah, just the reason I'm going to not do that for now, I just want to flip over to a website and show you kind of output of that. 1 second. I'm going to share screen, application, and right, it might go a little bit kind of meta for a minute. Can you see the map that's on the screen there now?
Yes, we can see that.
So this is the most recent flood outline analysis that we've done, and that was during the February storms, Kiara and Dennis, back in February, just before we went into lockdown. So this is a very extensive piece of analysis covering the whole of England on multiple different kind of satellite passes. So you can see the different colours here represent imagery from. So in blue, it's the flooding on the 21st. The 16th to the 18th of February. Then in red, it's the 10th to the 12th of February in 2020, and then the cyan colour represents the flooding from the 10th to the 18th. So that's the full, the combined flood outline that we produced from SAR imagery. Okay, gonna flip back to my presentation if I can. So almost seamless. There you go. So yeah, the other thing we're involved in is, in terms of kind of flood mapping with SAR, is trying to work out flood depths and volumes of water. So we do this for the purposes of kind of calculating things like required pumping of water. So sometimes we need to get in the heavy artillery from, for instance, borrowing pumps in from Holland. We need to work out exactly how many and what the size of those pumps need to be in certain circumstances. This is the Somerset levels in 2014. So we combine, effectively we're kind of combining SAR analysis of the extent with LiDAR analysis. So this can't be done in all places because of the kind of changing topography of the landscape as you kind of go downstream. But the Somerset levels lends itself pretty well to this kind of analysis because it's very flat. So we're currently exploring other potential applications within the EA, including soil moisture applications and interferometric SAR, looking at very fine scale land movements and substance, that kind of thing. So I don't know how much any of you know about SAR imagery, but just in case there's any kind of gaps in the knowledge in terms of how we can use SAR imagery and what kind of aspects of it we can exploit for flood mapping. The diagram just gives a very kind of simplified explanation of what you're actually seeing in SAR imagery. So this is an example of some SAR imagery. You see it's a pretty noisy image. And basically, where you have very dark features, it means you've got very little backscatter coming back to the sensor. So you can see an example here with water. Generally, it's a kind of mirror-like surface, unless it's very windy, which basically means that a lot of you get very little backscatter, and you get what we call specular reflection, where the reflection is tending towards going away from the sensor rather than back towards it. And then where you've got very bright features in the imagery, that's where you're getting a lot of backscatter, and that's tending to be relating to kind of surface roughness. So where you've got a lot of roughness in the surface, that's where you get a lot of backscatter, and hence the diagram here. There are more kind of complicating factors that come into play than this, but these are kind of the broad principles that we work on for flood mapping. So it tends to be that dark pixels are very effectively kind of shiny surfaces in relation to the pixel of the imagery, which is in this case around about 10 meters. And the bright pixels are they tend to be not water. Okay, so you can see a few things going on in this image. You can see some flood water around the kind of center, just off center towards the right, and then we've also got these lakes on the left of the image. Then the top right hand corner we've got an airfield. So all of those features are very dark and can be kind of interpreted as being effectively water, although we know that the airfield is not. So just going through some of the benefits of SAR imagery, one of the real key to why we use SAR imagery is that it works in most weather conditions. Although it's not very good in windy conditions, as I was mentioning before, the signal that you're seeing in the imagery is relating to how rough the surface is. And if you've got a lot of wind, that's going to create roughness in the water and generally give you a brighter signal, which hampers things somewhat. The other thing is they tend to be very kind of consistent data sets, and they're very predictable data sets in terms of we know when the data is going to be acquired, and generally know when we're going to be able to get hold of the imagery. We can generally get hold of it pretty rapidly after acquisition. Some of the limitations, as you can see, it's a very noisy data set, and that clearly kind of hampers the ability to get a nice clean output. It's affected by wind, as I mentioned. Urban areas and field boundaries tend to be very poorly mapped. So where you've got hedgerows, you get quite a kind of haloing around effect around hedgerows, which can kind of eat into the apparent floodwater in the output. So urban areas, unfortunately, they're some of the most important areas to us, because that's where all the people are and where all the risks are in terms of to property, life, and businesses. But unfortunately, it's really difficult to get a decent output within urban areas. So we tend to focus on rural areas at the moment until some better algorithms come along, if they ever do. The other thing is that outputs can be quite easily understood on that basis. So if you tell somebody you've got a flood outline, you need to really hammer home all the caveats that are associated with that. Otherwise, the data can be quite easily misused. So it's not good for things like property counts or for insurance claims and that kind of thing, for kind of personal properties or kind of urban businesses. We would ideally really love to be using Sentinel-2 imagery all the time for doing flood mapping, but unfortunately, it's most of the time it's cloudy during these incidents, and there's just a comparison a day apart between two data sets, Sentinel-2 and the Sentinel-1 imagery. There's a detail image there. So just a very kind of brief summary of the workflow that we go through. So we go through the kind of image acquisition process. We need to collect an image during the flood, and a good pre-flood image that doesn't have any floodwater in it. And basically, we use the two images to compare with each other and produce a kind of false color composite image. So we can either get these data from the EODS or the European Space Agency Sci-Hub, EODS, Earth Observation Data Services. And if we're collecting data from the ESA Sci-Hub, then we need to do primary kind of image processing, which includes subsetting the imagery if we don't want to process the whole of an image scene. Then radiometric calibration, applying a Speckle filter, and then auto-correcting to get the data map ready. And we then stack the two dates of image together into a single composite image. And I'll show you what that looks like in a tick. And it's both polarizations, VHVV, for both dates as well. Then we go through a kind of training sample selection process, collecting data points to train a classification with, then undertake the actual classification itself. We tend to use random forest classification for this. And then really crucially, GIS editing at the end of it, and then manual editing. So first of all, editing involves removing erroneous flood classification on things like slopes at the top of hills, in urban areas and forests, that kind of thing. And then we really need to do manual editing at the end of it to make sure that that the product is good to send out. I was going to I think I'm going to skip through these steps. Really, it's this kind of step-by-step kind of guide in some ways. Well, this is just an image of the ESA Sci-Hub, then subsetting in using the snap tools, And then we, just highlighting that we're using both the VH and VV polarization for the SAR imagery. Then the speckle filtering, we tend to use the Lee filter with a 7x7 window. And then Ortho-Correction, masking, we don't mask out areas without elevation. Then, this is the SAR imagery itself. I showed you this imagery before, and I'm just going to show you now the composite image with the two dates stacked together, and it looks like that. So this is really exciting because all of a sudden you can see the difference between flood water and permanent water, and also between flood water and the airport as well. So the runways, the tarmac surfaces. So the flood water is fortuitously in this particular instance highlighted in blue in this false color composite. Then that as you can imagine, makes it much more straightforward for kind of doing automated analysis of the imagery to pull out a differentiation between floodwater and permanent water. And then highlighted in yellow, there is the floodwater extracted in this image. And there it is, just overlaid on Ordnance Survey mapping. And that's me. I hope you found that interesting. I'm very happy to take questions. A bit of a whistle-stop tour. And I know that we've got quite a lot of things to get through. So, yeah, that's me. Thank you very much for listening.
That's fantastic, Crispin. And it's the topics you covered are actually perfect for today, because I'm going to elaborate more on how microwaves interact with surface features. So you've given a fantastic intro.
I'm going to stop sharing my...
Pick up on the questions, or can you see the questions, Crispin?
I don't mind reading them out if that helps. I've seen that we have had a couple come in while Crispin was talking. So the first one, I think it's both from Natural England as well. So how do you decide on the polarization? Why have you chosen VH in this example over others?
Oh, we use both for the classification. We use both VH and VV.
Okay, so that was just in the example on the slide, I guess.
Yeah, that's right. Yeah. So in the false color composite, that was a 3-band image, just for display purposes, which I think was VH in the pre-flood image, and then stacked with the VH and VV from the flood image.
Okay, thank you very much. And another question that's come in is, have the Environment Agency looked at the use of Sentinel-1 to monitor soil moisture in peatlands?
I don't know, to be honest. I'll go and find that out, to be honest, if that's okay.
Okay, you could let us know in a future meeting, put it in the chat in a future meeting if you find anything out. And I will post a link to our soil moisture outputs in the chat a bit later on as well, because we had the workshop on monitoring soil moisture using Sentinel data. So I'll put that in as well. There's also one that's come in. What is the threshold for wind speed before it affects the quality of a SAR image or analysis? So you were saying about it ruffles the surface of the water and gives it more, kind of topographic roughness and makes it look brighter in backscatter than it is. Do you have a threshold for wind speed?
I'm afraid I don't. It's something we could look into. It's not very straightforward to look into, because you need kind of continuous wind speed measurements in places where you've got flood water to be able to get any kind of accurate kind of analysis of that. But you could probably do some kind of generalized analysis, which we haven't unfortunately done yet. But yeah, it's just more of a kind a kind of a caveat, just a warning really, that if you got really kind of windy conditions, then the quality is going to be reduced, and you just need to be aware of that.
Okay, thank you very much. I suppose if you think about things like fetch as well, it's going to maybe differ in some areas than others, and the depth of the water. We've also got a question: how far can you go back and get the data for? So can you look at past flooding from years ago?
Yeah, so the SAR imagery with Sentinel, with the Sentinel program, goes back to, I think, 2015 or 2014, and so we could go back into the archives of the Sentinel imagery. As far as I'm aware, that's the only type of SAR imagery that's routinely captured. So apart from that, if you want to go further back, then you'd have to kind of look at satellite sensors that happen to be captured during flood events, of which we do have quite a lot of kind of examples where we've invoked the International Disaster Charter to collect SAR imagery during incidents in the past, especially before the Sentinel program. So we've been doing this kind of analysis with SAR imagery probably for about 10 years or so now.
Okay, thank you very much. And then we've got a question: do woodlands tend to lead to similar output problem artifacts as hedges do?
Yeah, it's not easy to see through woodlands, to be honest, with this kind of imagery. So we tend to mask woodlands out. It's possible we could do analysis like we've done on the Somerset levels, if the landscape lends itself to it, i.e. it's kind of relatively flat. We can we can identify the edges of floodwater where we know it definitely, that is definitely the edge, and then identify the height of those the elevation of those edges using LiDAR data, and then run some interpolation across the LiDAR surface to kind of fill in the gaps. But it is fraught with danger in most parts of the country, to be honest, because of the kind of changing topography as you go downstream.
Okay, thank you very much. And then we've got a question of how long is the time period between acquiring an image? Sorry, how long is the time period between acquiring images, i.e. the return period to a given location? So about the orbits of the satellites.
Yeah, so it's very frequent with Sentinel-1 imagery. Fortunately, it's once every either 1 or 2 days, I think. The repeat orbit is actually once every 6 days, because you've got 2 satellites kind of orbiting in tandem, two kind of twin satellites. Each one of them follows the same orbit every 12 days. So you top that up, so you get once every 6 days. But because of the overlap between orbits, and because you're getting ascending and descending orbits, that it brings down the return period for most parts of the country to 1 or 2 days.
Okay, thanks very much. And you're using both ascending and descending orbits in this?
Yeah.
Yeah. Okay.
Whatever we can get our hands on.
Okay, thank you. I think that was the last question. I just had a follow-up to that one about the speed of acquiring the images. You mentioned using the DEFRA EO data service or the ESA Sci-Hub. Are you using the EO data service now for this? Because that obviously you've been doing this for a while, and the EO data service was just launched earlier this year. Are you starting to incorporate that?
Yeah, we tend to use that for not for the kind of rapid response service at the moment. So if we're kind of doing slower analysis, then we'd use the EO data service.
Okay, so you are using the analysis ready data processed by it, but not yet on the rapid response.
Yeah.
Okay, thank you very much. I think that's all the questions that have come in. Crispin, are you staying around for the whole session? So if anyone thinks of another question during, they could perhaps ask during the next Q&A session.
Yeah, sure. Yeah.
At the end. Okay, that's fantastic. Well, I think I will then hand back over to Iain then. Thank you.
Okay, thank you.
Great, thank you. That's really good. So, in fact, some of the questions that people are asking is perfect timing, because that's some of those things I'm going to pick up on, especially in terms of how the microwaves interact with the surface. So the key topics that I'm going to cover today are essentially it's the microwaves interacting with the surface. What are the key drivers of that, and help you understand a little bit more about, when you look at an image, what it is that you're actually seeing. But first, if you remember, what I was going to do on the kickoff today was to cover just a few slides on what I call the core concepts. So if I just share my screen. And go to here. Okay, so you should see some basic concepts. So these are things that come up often, and typically they get skipped over sometimes when you do a course introducing you to radar or introductory remote sensing courses or books, and then when you go and start to look at the radar data or the literature, you find that some of these things kind of creep in, and they often don't offer much of a explanation. So one of them very quickly is radians. So radians are used often in the context of radar, and that's largely because as we talked about on Monday, is that the history of the electrical and electronic engineers coming from the context of telephony and it being very driven by an engineering, physics and maths kind of community, and rather than the applications community. And a radian has a more mathematical elegance to it that makes it worthwhile discussing. But very quickly in the chat, because the chat doesn't get recorded, so you don't have to worry about that. Does anybody want to type in a few reasons why we might divide a circle into 360 degrees? So I'm guessing that you're all familiar with the idea of splitting up the angles through a circle into 360. But anybody want to hazard a guess of why 360? Because it is entirely arbitrary. You could have we could decide to suddenly make it 100 degrees in a circle. And go 100% metric. Yeah, so Helen and Paul have jumped in there. So multiple divisors. So in terms of the things that you can divide 360 by, well, 1 clearly, but 2, 3, 4, 5, 6, 9, 10, 12, 15, 20, 25. It makes it's really easy to work with that set of numbers of 360. If you're a mathematician, though, you want something that's a bit less arbitrary than that. And the way that a radian is defined is by taking a circle of radius r. And what you do is that you can imagine using a piece of string and a pen to draw that circle. And then you take that piece of string and you lay it around the circumference of the circle you've just drawn. And the angle that makes at the center is equal to one radian. So it's called radian after the radius. And because the circumference of your circle is 2 pi r, that's why you have 2 pi radians in 360 degrees. So in one full revolution. And that will come up. It will come up in my diagrams. It will come up in textbooks and literature about radar. Is that people will default to using radians very often. So it's worthwhile you know where that comes from. We touched on logarithms and decibels on Monday, just in terms of how we've inherited the decibel. And this is just a quick revision for logarithms and for one particular reason that I'll mention in a second. But and when you get these slides, you'll be able to go and revise them all. But in terms of essentially what the logarithm is the inverse of the exponent. So the logarithm to the base 10 of 10 to the power of x is equal to x. So, and in the radar context, the logarithms are all to do with using decibels. So we're typically using log to the base 10. And in terms of a few numbers, so looking down the list here in terms of if you're doing decibels, so it's in base 10 logarithms. A key thing to note here is that your 0 point in your graph actually starts at 1, and you never get to 0 in your graph because that's minus infinity. So that's all the way down off the bottom of the page. And that's actually quite significant when if you recognize that 0 decibels is equal to the number 1. And when you're looking at quantifying the signal that you get, when you're plotting it in decibels, you will notice that you mostly are into minus numbers. If you go into plus numbers, then the amount of backscatter you're getting back is more than you would expect from a non-directional scatterer. So you're getting more energy than you would expect back if you start to get positive numbers in your signal in decibels. Most of the numbers you'll deal with are actually minus numbers. And then the other important number to bear in mind is that a factor of 2 is approximately 0.3. So positive or minus, depending on whether it's 2 or it's 1 over 2. But that's where the 3 dB beam width, for example, or 3 decibels comes in, because the decibels is 10 times that number. And so 3 dB is a very common way that you can use to read graphs, is that 3 decibels is going to equate to a factor of 2. And as I mentioned on Monday, your logarithm to the base 10, you can't take the logarithm of a number that's in units, so you have to divide the quantity you're interested in by the reference quantity. But you can always make that reference quantity 1, and therefore you're just taking the logarithm of the quantity. Now, one of the significant things about the fact that data can often be scaled in decibels is that if you take an image and the data is scaled in decibels, and you apply, say, a mean filter. So you apply a 3x3 filter that just takes the arithmetic mean of the 9 numbers in that filter. If you're taking the mean of the logarithmically scaled data, you're actually taking the geometric mean of the data, not the arithmetic mean. The geometric mean is when you multiply n numbers together and you take the nth root, whereas the arithmetic mean is the adding n numbers and dividing by n. Now, interestingly, there is some value in the mean, and you can use that as an indicator of heterogeneity or variability across a collection of pixels if you look at the ratio of the arithmetic to the geometric mean. But I'm just reinforce here that you've got to always be careful when you're dealing with radar data, is that it will very easily, you'll find that you're working in decibels and not realizing it, and you try to apply maybe things that you thought would be a good idea, and they might give you an image that looks nice, but you might actually be changing the numbers in a way which is less meaningful. And often you'll get the choice between decibels and digital numbers, and one of the things we'll do in Earth Blocks next week is look at the histogram difference of whether you look at decibels or digital numbers. The other quick thing is just to try to put you at ease, is that you will come across references to complex numbers, and not to be too worried about that. So complex numbers come from the mathematics of looking at the square root of -1. When you're not familiar with looking at this, you often think immediately, the first thought that comes to your mind, if this is the first time you've seen it, is, oh, well, the square root of -1, is that not just -1? And then you suddenly think, oh, -1 times -1 is +1. So what's the square root of -1? And the answer is, we don't know. You have to imagine that there is an answer to that. And that's why it's an imaginary number if it has this lowercase I, which we represent to be the square root of -1. There are some very neat tricks that you can do once you start using complex numbers. You don't need to know them all. I just want to make sure that you kind of understand where it comes from. But one of the things that you can do, well, with dealing with complex numbers, is that you can have a real number like A, and you can add an imaginary number, and you know it's an imaginary number because it's got lowercase a times b. So b is a real number, but when it's timed by the square root of -1, it becomes an imaginary number. And this real and imaginary combination is called a complex number. And the thing is that complex numbers, the real and imaginary components, can never mix. They're not interchangeable. So you always deal with just the real part and the imaginary part separately. And that's very like how we deal with Cartesian coordinates. And on Monday, we looked at how we can use Cartesian coordinates to represent a wave. So a wave of a certain wavelength and phase is represented by this orange vector that's rotating round. And our complex number of A plus IB, we can represent it in this space where A is our real number and B is our imaginary number. And then we can use complex numbers and all the mathematics of complex numbers by using the A and B. And remember, that's the phase of our wave. So you will find that there are times that you get given data, and in SNAP, you will sometimes see that you can choose between looking at the real or the imaginary component. So what's often referred to as the I or Q channels. So the way that the wave is stored and recorded in a radar system is they store it as a complex number. So they have a real component and an imaginary component. Once you get that, you can actually just forget about complex numbers and just realize that it's just the Cartesian coordinates of our vector that represents our wave. And when you have that, then you can go from Cartesian coordinates into polar coordinates and have the length or the amplitude of the wave and the phase. So in SNAP, you can actually look at those two different properties. You can look at the two channels, because you remember that they're in a radar image, every pixel has got two numbers in it. It's got a real and imaginary part, or it's got an amplitude and a phase. They both describe the same vector, which represents the wave that is recorded. And much of all you're looking at is the amplitude of the wave, not the phase. And the last thing I'm going to just to mention, so that everybody's up to speed with it, is the Doppler shift, which I'll talk about on Monday in terms of how that has an impact on radar. And the key thing, hopefully this little animation will work, is that a source that is transmitting a wave, as it's moving, that in the direction, oh, that wasn't, play that again, is that in the direction of travel of this wave, it's essentially catching up with the waves that it's transmitting. And so the frequency of these waves are much higher than the waves behind it, because this source is traveling away from those waves. And this, in audio terms, is what creates the change in pitch as a vehicle drives past you, because you're going from high frequency as it's moving towards you. So if you're at this side, and as it passes you, it ends up going to a lower frequency and the pitch changes. The actual transmitter here is simply transmitting the same waves equally in all directions, but it's catching up with its wave in one direction, and it's running away from those waves in the other direction. And so from the observer watching this object moving, or this transmitter moving, is that you hear that pitch change. And the colloquial language for that is it's blue shifted if it's going to higher frequencies and red shifted if it's going to lower frequencies. And that's just reference to the frequency or wavelength ranges across the visible part of the spectrum. And the original term for red shift comes from observations of distant galaxies, where they could tell that the distant galaxy seemed to be traveling away from us because it has a red shift. But this is where it comes from, is because it's going to longer wavelengths and therefore shifting down the visible part of the spectrum to the red end. Right, let me come out of that. If there's any quick questions on that, type them into the chat while I transfer over to my next slides. And I'll have a quick look in the chat. There's nothing. So that was just a little bit of a background, because you will come across those terms if you start looking at the literature or start playing with things like SNAP. And even if you didn't get it first time round, you've now got something to refer back to. Right, so day 2. So we had Crispin, which was a fantastic introduction. We've done the core principles. I'm now going to look at how microwaves interact with surfaces. And that's just a reminder that we are recording this session. And I had to quote you, Crispin. I don't know if you are still on the line. So I hastily put this slide together. Outputs easily misunderstood, which is essentially the focus of today's lecture, which is trying to help you know how to better understand these images. And a week today, so next Wednesday, we will actually start to look at some data, and we'll split into two groups. So people who want to do some things in Snap will do some stuff in Snap. And those of you who are more interested in just in quick looks and trying to understand visually what's happening in the data, will use Earth blocks for those people. Now on Monday, that's also a reminder for me to, in terms of a bit of housekeeping. On Monday, I will be checking all the people's email addresses for access to Earth blocks on the Wednesday. So if you are definitely going to be here next Wednesday, but you think you might not be here on Monday, please let myself or Paula know that. Okay, so surface scattering. And by surface scattering, in the first instance, I mean not really any vegetation on it. So let's just look at surface scattering to begin with. And then if there's time today, I'll do it, or first thing on Monday, we'll look at the scattering specifically from vegetation. And vegetation lies on the surface, but I make this, I separate it slightly because vegetation starts to become more three-dimensional rather than just this of the Earth. It's adding a three-dimensional component to this scattering. Now, getting back to, I'll probably show this slide on the beginning of every day, insofar as I keep emphasizing that this is the key takeaway for everybody, is that this is how our imaging radar system works in terms of collecting the scattered echoes as a function of time, and then making an assumption about that being in proportion to the distance across the swath, across the ground. And specifically today, we're down at the surface level here. So these 4 dots I have are just scattering the energy equally in all directions, and that's not necessarily the only thing that is going to happen. So we want to look at the scattering properties on the surface. And the 2 key things that determine how much energy we get back to our radar system, and therefore how bright a pixel will look in our image, is how much energy does the target scatter, and which direction is it scattered in. And it's important that you really understand that those 2 things are the major factors. And if anything, the second factor there is probably more dominant than the first, and also is a bit harder conceptually to sometimes to understand. So I'll actually show a fairly simple graph later. Somebody was asking about soil moisture. There's a relatively simple relationship with soil moisture, which is that if you add more liquid water content to soil, it will scatter more microwaves. And that's the end. There's nothing more complex than that. The complexity comes from the fact that there are also other factors that change which direction that energy is scattered. And we're going to have to think about that much more closely. It's the same with vegetation. If you add more water into vegetation, into the structure of the vegetation, it will scatter more. And I'll talk later about how it's really important that we recognize that it's liquid water, not frozen water. So let's look first of all. So the direction, it's a relatively, of these 2, the first one is relatively more straightforward to comprehend. You change the properties and it scatters more energy, and it would look brighter in your pixel. But let's look at a minute about what happens in terms of the direction in which we scatter. So this little animation, if you went to the intro to radar.com, you would find the animation here. You can play to your heart's content on that. But I've got 3 examples. The first example is what's called the isotropic scatterer. So this is our radar system, and we're going to transmit a signal. It's going to hit our target. It's going to come back. We're going to measure the response. And this first target, what we mean by isotropic is that the energy that arrives at the target is then scattered equally in all directions. It's got no preference for the energy. So in the cartoon, the little animation, I've tried to represent that, because if you look at the orange circle that's rescattered, it's the same size in every direction. isotropic scatter is actually an important one because that is our reference point for quantifying the normalized radar backscatter. So our measure of how much energy lies within a pixel is based on the assumption that it is isotropic, and then saying, well, if it was isotropic, how much would we get back? And if it's the same as we would get back from an isotropic scatter, we'll call that 1. And everything else less than that will be less than 1. So in a decibel scaled graph, that's going to start off at 0. At the 0 line and below in terms of decibels is a scatterer that is much more like this redirected one. It's scattering energy not as good as a perfect isotropic scatterer. So one of the things that this isotropic scatter could do, it could actually absorb some of the energy, and then it doesn't scatter very much energy. But at the moment, we're just assuming that all the energy is scattered. So in this case, for the isotropic scatterer, the scattering is, it scatters all of the energy, and it scatters it equally in all directions. This second case, the redirected one, is that it still scatters all the energy, but it scatters it down the way. In this particular picture, you'll see that it actually, from the animation, you'll see there's almost nothing in the upward direction, and almost all the energy is scattered in the downward direction. So this particular scatter is redirecting the energy away. And one of the key examples of what that happens in a radar image, Crispin had an example of both water, but also the runway surface. And the key thing about them is they're both smooth, and therefore you get a very strong specular scattering. It scatters it, it redirects the energy, actually scatters a lot of the energy, it just scatters it in the wrong direction. And up the top, we've got a bar that's just to indicate the fact that our redirected return is much less. The total amount of energy is the same in terms of the scattering, but it scattered it in a different direction. And our last example here is something that's really good at giving you backscatter. So you'll see that there's very little that gets scattered in above or below or to the right, and most of that orange band comes back to the sensor. So we get a much brighter target. In audio terms, if you're listening for the echo, you get a much louder echo. And I'm going to look at some particular examples and explain a little bit more what the implications are of things that are really good at backscattering. Now you'll notice that in terms of where it comes in higher than the isotropic scatterer. And so the backscatter that would arrive from this target is actually in decibels is going to be larger than 1. So it's actually a positive number. And we do get both natural and artificial targets on the Earth's surface that will do that will actually preferentially scatter energy back to the radar system. And that's just the reminder that all the energy that the target is scattering is the same for all of them. It's just that it's the direction that it scatters in has an impact. And one nice example, anybody want to quickly identify the geographic location? Stick it in the chat. Give me a chance to have a mouth of water. Barbados, very good, Stuart. I think Barbados, yesterday I was in Barbados, so I'm doing some training this week and next week also in Barbados. Unfortunately, I'm doing it from this same location and not actually sitting on a beach. But the little advert for the Barbados Tourist Board is that I believe at the moment, because so many people in the UK are working from home anyway, they've extended the period of time that you can go and have a visitor's visa. So you can essentially move yourself to Barbados and spend lockdown in Barbados and doing all your Zoom meetings and everything from the beach. It sounds very appealing, but they were telling me yesterday that it's raining a lot, so it's not always nice and sunny. But I show this because I'm going to. Yeah, Stuart's saying where do I sign up exactly. There was a question that came in. From Ian, how do you know how much energy is redirected, scattered, and how much is absorbed? And the short answer to that, Ian, is that you don't. All you get back is the signal that arrived back in the sensor, and so that's why that's exactly why Crispin was pointing out that it's often quite difficult to interpret the what you're seeing in a radar image. And so I'll elaborate a little bit more on that shortly. But I wanted to show this. The convenience is that it's an island. And when I click through some of these pictures, you will see that the island itself stays pretty much the same, but the water surface around it is dramatically different. And in terms of liquid water, pretty much all the energy that arrives at liquid water gets scattered off the surface of liquid water. So if you've got, if that's conveniently blue, if you've got a body of water, all the energy that arrives from the microwave radar is going to be scattered. So the scattering that comes from liquid water, in terms of the impact that it has on what you see in the radar image, is all about the directionality. It's all about where is that energy scattered to. When it's really dark, I'll come to that in a second. Where it's really dark, so some of these very dark features here is probably because it's much smoother. And so if it's smoother, all the energy is being scattered off in the opposite direction. Where it's brighter, and some of these areas get very bright, it's because the wind is roughening the surface sufficiently that you get a bright backscatter. So it's all about surface roughness, and that's why I'm going to talk about surface roughness first. And then interestingly, just zooming into here, you will see that there's a trail of dots that curves around, and I've identified a small section in orange, and we're going to zoom in. And if anybody has got, anybody want to hazard a guess of what we're seeing there? Oh, and Helena has conveniently shared the link to barbados.org if anybody's keen to follow up that offer. Nicholas has said ships, so I'm going to show you a picture of ships in a minute, and they will look a little bit different. These have a very distinctive kind of almost like a teardrop shape, and they're all consistent, and they're in this big pattern. Floating gin palaces. I'm not entirely sure what a gin palace is actually. Oh, well, lots of ones coming in. Whales. So whales is a good guess, but it's not whales. But Karen gets the prize for is sargassum. It's lumps of sargassum seaweed, which is a real problem in the Caribbean, and there is some there's some interest in being able to use SAR to monitor sargassum because of the fact that we can see through the clouds. So and the key thing is that it floats on the surface, so it has a significant roughness impact on the surface, and that's why we see the scattering coming back from it. Ships will come back to. I don't have examples of whales, unfortunately, but ships will definitely come back to. Right, so this diagram, I'm going to explain it, and then I'm going to try to illustrate it with the use of a laser pointer, and then I'll come back to it to sort of reinforce it. But let me just quickly explain what's going on in this diagram, first of all. No, laser pointer in a second, hold on. Getting ahead of yourself, I'm just trying to get the annotations up. What we're seeing here is that I've got two axes. This is essentially a graph. And so the x from left to right is increasing surface roughness. And the y-axis from bottom to top is increasing incidence angle. And by incidence angle, just to be clear, the incidence angle is the normal, so the perpendicular to the surface, and then it's this angle here. So that's my incidence angle. So it goes from essentially zero incidence angle down the bottom here to a slightly bigger incidence angle to a larger incidence angle. And then across left to right, we go from a almost perfectly flat surface to a sort of a rough surface to a very rough surface. And what I'm trying to show in these diagrams is that the incoming line, if you haven't noticed yet, by the way, just as a short aside, is that what I try to do is I make every single radar diagram that I show, it has the signal coming in from the top left So the radar system's up here, transmitting down to the surface over here. And I try to draw every diagram in exactly that same standard configuration, so that it's re-emphasized. So if in doubt, you can assume that that's the configuration that I'm using. And so the radar signal comes in from the top left here. It hits the surface and it scatters off. When it's a perfectly smooth surface, all of the energy is going off in the specular direction. But when it starts to get rough, what I've got in this blue line here is trying to represent the shape of the energy, of how much energy is scattered in different directions. And the red arrow is specifically identifying that contribution. So the red arrow is specifically trying to identify the contribution that is coming back to the radar system. So that's what the radar system will detect. And what we see is that if we take the middle one, for example, as we get rougher and rougher, the amount of energy that is scattered back to the radar system increases. If we go to very large incidence angles at the top, it's also the case that as you get to higher and higher roughness, is that the amount of energy that's scattered in your direction increases. And that's because when we're at this scale at the end here, it's close to what you might refer to as a Lambertian scatterer, if you've come across that in optics, is that it's so rough that it scatters the energy equally in all directions, regardless of which direction the beam comes in. So this red arrow is the same pretty much for all three cases of incidence angle. But as we go to the case in the middle, as you go to shorter and shorter incidence angles, you actually get a brighter response from the target, or the target area on the ground. So the key thing here is that the incidence angle does have an impact, and this is part of the reason that what Crispin mentioned about it sometimes being difficult to interpret radar images is it has these annoying properties, which is, well, if the incidence angle and the roughness both have an impact on the signal that I measure, then that introduces a degree of complication that that makes it difficult. So you have to know the local incidence angle. So the local incidence angle meaning not across the entire swath, but on an upslope and downslope might have a different local incidence angle. The roughness is going to have an impact, and also how much the surface is actually, how good it is at scattering versus how much it might be absorbing. And my way to illustrate these three cases is I'm going to come out of the sharing just now so you can get the full screen of me. Asked in the chat about whether you could pick up plastic. I have not seen anybody pick up plastic, but interestingly, in my undergraduate class that I teach for geography students at Edinburgh, or geosciences students at Edinburgh, one of the things I get them to do is that they do a mini Earth Explorer mission proposal. And it is always at least 30% of the student groups, the teams that put together a space mission proposal, are trying to measure ocean plastic. So there's lots of interest, and there's lots of aircraft-based measurements of plastic in the oceans from lasers and optical and radar. I've yet to see a convincing example of radar being used to actually monitor. And part of this, the problem is this ambiguity is that, well, lots of things can cause roughness on the surface or changes in roughness. So oil slicks, for example, will flatten the surface and stop the waves, and therefore they have a high contrast with the surrounding water. So artificial oil slicks will do that, but natural oil slicks from the things like algal blooms. So somebody had been asking about algal blooms before, is that algal blooms can emit oils that actually then dampen the waves on the surface, and that causes a signal that looks much the same as oil slicks. Question that came in: do ascending and descending orbits influence the incidence angles? So we'll hold that thought, Duncan, because I've got a graphic that's going to illustrate that. But what I wanted to quickly show, this is a laser pointer. And I can use, one of the things I'm going to use, this is my diffuse scatterer. It's a collection of transparent, I'm going to come back to that when I look at vegetation. They're semi-transparent or translucent sheets, and I've got a whole pile of them together. So these are going to be my sort of very rough scatterers. And I've also got my specular scatterer, which is just the screen of my phone. And I've got a laser pointer here. And what I'm going to try to do, this is going to be a bit awkward, but I'm going to see if I can manage it, as I'm going to turn my monitor around so that you can see, and I'm going to turn off some of these lights. Because hopefully what you can see is if I point this laser pointer at the wall, see, that might be too small. I might have to use something else. Let me use this envelope. So here's my, I'm fairly sure you could see that on the screen. So turn that back. If somebody can type a yes or something that you can see the laser beam on the piece of paper, then I know.
Yeah, we can see that. Yeah.
Yes. Okay. Now, if I have my perfectly smooth surface, which is the glass on my phone, is that if let me just get that into shot. I'm hoping that you can see that I can reflect it off the surface. So the laser beam comes off the glass and hits the surface, so you can see it on the paper, especially if I move it around. But you can't see it. You can't see it on the glass of my phone. If I replace the glass of my phone with this little box, which has got a sort of semi-glossy surface, is that if I fire the laser beam onto here, you should be able to see that the laser beam reflects off that surface. So there's definitely a specular reflection component because the laser beam is now on the white paper. But if I get it just right, you can also see, the laser beam actually on this little packet. So it's got a contribution, which is a specular reflection, which is going onto the piece of paper, but it's also got a contribution that's just coming from this surface. My final version is if I've got my sort of diffuse scatterer. Let's see if I can hold these all together. Is that if I scatter off the surface of here, you will be able to see it on the surface. So you can see the laser beam on there, much the same way. In fact, the easiest way is just to fold that in half and do it in an envelope. Is that if I try to reflect it off one piece of the paper, it's not going to work. It doesn't give me a reflection. I can't see anything on the reflected part up here. I don't see a reflection of the laser beam. But you can see the laser beam scattered coming off the piece of paper. So that energy of the laser beam is hitting the paper and it's going equally in all directions because I can see it, you can see it. So everybody can see that. So that's the case if I go back to my diagram. Bear with me a second. Back to desktop 2. So the 3 cases we've got here is that my phone screen is like this case over here. It's very smooth, and I can reflect the laser beam off the surface, and I can shine it onto, and I'll see the dot appear on the wall or on the piece of paper behind. If you've got a laser pointer at home, of course, you can all go and try this and experiment of how it scatters off of different subjects. When we look at the extreme version of the case of the very rough scenario, when it's really rough, the energy is scattered equally in all directions. So it doesn't matter which direction that you look at, you will see the laser beam appearing on the paper. Whereas the after dinner games, it's called, but that little box that was semi-translucent had one component that gave you a little beam on the paper, but it also scattered some of the energy in multiple directions so that everybody could see it on the piece of paper or in the box. So these are the three extreme cases, and it's exactly what we get in the context of radar imagery. And we have to be very conscious of the fact that the incidence angle, so the angle that you're observing it at, and the roughness can have a big impact on what we're seeing. So what constitutes rough? There are different definitions. The standard definition is this Riley criteria. I won't explain in this course where that comes from. The key thing to note is that you've got two terms. You've got an incidence angle in here, so incidence angle has an impact. But the key thing is that you've got a wavelength that of the electromagnetic radiation that you're using, and you've got an H. An H is the root mean square height of the surface. So it's one measure of the roughness. The roughness, the key thing is that rough is relative to the size of the wavelength. So it's a scale factor. It is not a completely objective quality of the surface or the scatterer that you're observing. What it is a scale factor relative to the size of the wavelength. So if I take this image on the right of the rough surface as just the same picture that I created on my computer, and I just made it smaller, and these waves are just smaller, the same proportion to the waves on this left-hand image. So we've got shorter wavelength and shorter root mean square height, you'll get exactly the same scattering pattern. So what constitutes roughness is entirely dependent on the wavelength that you're using. And that's another important thing now that you've got access to potentially X band at 3 centimeters, C band 5 or 6 centimeters, L band about 23 centimeters, and then up to 70 centimeters for the P band and the biomass mission that will be coming soon, is that you've got a range of wavelengths to choose from, and your interpretation of the imagery is dependent on those wavelengths, because they'll look different at different wavelengths. So that's our take-home message from that section there. Incidence angle is important, and roughness is a matter of scale to the wavelength, not an absolute property. I've just got a couple of nice examples here in terms of the. Oops, sorry, my mouse is very trigger happy. This is actually the eye of the storm of Typhoon Idai. If you remember, back in March 2019, there was a large typhoon that came into it made landfall in Mozambique, near Beira, along here, caused enormous devastation in terms of the flooding that it caused inland. But what I'm focusing on here is just that it's a lovely example of how the roughness is the big factor here. So within the eye of the storm, where the wind has dropped considerably, the water is all smooth, and as you just get outside of the eye of the storm, the surface is roughened considerably. So you can see the general pattern of the surface roughness there. And that is that's across all the oceans, and that's where, from an oceanographic point of view, C-band has always been preferred because it's very sensitive to many of the roughness features in across the ocean surface. Now, before actually no, I'm going to skip on. I'm going to take a break in a second just to take a glass of water. But this diagram, this one's more for your reference once you get a copy of the slides, which is looking at the change of incidence angle. So the incidence angle is changing from here, so at 15 degrees, and then going all the way out to 55 degrees. So 15 to 55 degrees is about the biggest range that you're likely to see in imaging radar. We always have to look obliquely, remember, because we need to make sure our range measurements are roughly in proportion to the distance along the ground. And any single radar image from space will tend to have a fairly small range of incidence angles. But airborne systems or multiple imaging modes from different satellite imagery will have might have as big a range as this. That also illustrates, by the way, one of the reasons why the military has always been interested in imaging radar is because it's side looking, is that you can fly over a border. So the border might be here and you can fly in your own airspace while imaging across the border. And that's why sometimes some of the data that you might come across, if it's a system which is partly developed with the military in mind, is that airborne systems sometimes will have very high incidence angles. And this is why, is because they've got a particular motive to have a very large incidence angle because they're looking much further away from where they're flying. So these were the three cases in terms of very smooth, intermediately smooth, and very rough that we just looked at. And I've got a section coming up in a minute that will talk a bit more about the vegetation and how vegetation impacts on the signal. This unusual scatter is going to come under the heading of unusual scatterers that I'm going to talk about in a second. But this is what we refer to as Bragg scattering. And it's because if you have a very regular surface, what you get is, depending, if you get the incidence angle just right, all the scattering from each of these waves will come together and combine. So that if each of the scattering from each of the tops of those waves, if you remember when we looked at the combination of waves, is if all of them come back combined, then they add together to create a very large signal. If they come back and they're all out of phase, the signal will be very low. And if you just get the geometry just right, you get a very, very bright target. I'm going to show you an example of that in a second. I'm also going to show you a little animation that's going to illustrate essentially these three cases at the top. Although when you get to a very rough surface, the distinction between a very rough surface and a surface that's got a thin layer of vegetation on it, it's very difficult to separate those out, because vegetation essentially acts as a roughening feature in terms of the way that the microwaves interact with the surface. Oops. And that's just zooming in and looking at a bit more detail in terms of what the trends might be. So what does that mean? So that example, so a very, very smooth surface, a medium rough surface, and then a very rough surface. I've tried to encapsulate that in this animation. So, whoa, sorry. Let me just pause that for a second. So what I'm looking at here, this is a grid of pixels sort of matched onto the ground in terms of what you might see as a radar image. The three cases here, we've got a very smooth surface. It's not perfectly specular. You'll see that from the animation, but it's very, very smooth. In the middle, we've got a rough surface, and then we've got a really rough surface at the end here. And these three panels at the top, they're showing you what you would see if you looked straight down and got energy scattered back. So you got, if you're looking straight down at it at a very small incidence angle, this patch of ground here is going to look really bright. So when we take it back to how we start off, is that this is us looking straight down on this grid of data points on the ground. And number one here is very, very bright. It's a very strong specular reflector. So if we look straight down, if we have a signal that was going straight down beneath us, like an altimeter, it gives us a very bright target because the surface is very smooth. But as we go on, as we increase the incidence angle, what you'll see is that drops very quickly and it becomes, it's black. So that's the scenario we have with runways and tarmac and flat, smooth water surfaces, is that it's still scattering lots of energy. It's just, it's scattering it in the wrong direction. Sorry, when I do the annotations, I keep forgetting that I have to go back to the mouse to switch it back. In the extreme rough case, what's interesting here is that it pretty much looks the same from every direction. So that's like the laser beam off the paper surface, is that it doesn't matter which direction you look at it, it still looks the same. And the one in the middle is the one that flips over. So if we look at the let me clear all those drawings and then go back to the. So the specular surface drops off really quickly. The rough surface drops off slowly. So by the time you're looking at it at this shallow angle, the very rough surface is the same as it was right at the beginning. The rough surface is darker than it was at the beginning, and the specular surface is very much darker than it was at the beginning. But you'll notice that there is a point at some incidence angles where they all, if I get, that's probably about the one that they're looking all the most similar. And that's where it becomes mostly problematic. So that question earlier about, how do you know how much energy is being scattered in the other directions? And the answer is you don't. All we're getting is this signal of how much is scattered back to the radar system. And sometimes at given incidence angles, two surfaces which otherwise look different in some circumstances might look the same in other circumstances. So when I move to this incidence angle, for example, my rough surface and my very rough surface look almost identical. And this is purely because of the directionality of the scattering. Nothing else is changing. So we're changing not just the absolute values, but the contrast and the relative values of these different surfaces based on different look angles, or the incidence angles in terms of the way that we're looking at them. Now, this is the slide that I mentioned earlier, which is the straightforward relationship between soil moisture and dielectric constant. So the dielectric constant determines how much energy is scattered, so how much is absorbed and how much is scattered. And it's the diagram that gets everybody excited when they're looking at moisture with radar, because they say, well, that looks fantastic, because as the soil moisture increases, the dielectric constant goes up. The big challenge, and I haven't had a chance to look at Paula's report yet, so Paula's actually shared a report. Oh no, that was about the ocean plastic. You mentioned though that you were going to share something, Paula, to do with the work that you've been doing. Oh, you did share it earlier. Yeah.
Yeah, that was a link to outputs from the workshop. So there's videos and presentations, and there's possibly just a report about the workshop itself.
Excellent. So if you scroll up the chat, you will find Paula's link to the workshop that was looking at Earth observation for soil moisture. And it's always been, since I shared an office with somebody called Puvelin, who was a soil moisture expert, and his PhD was all about trying to detect soil moisture. And I used to go out in the fields with him and use a TDR probe, stick them in the fields to do his fields data collection. And it was always, it's very clear that it's not as simple as it first looks. There has been some very clever stuff to do with different polarizations to try to accommodate the changes in roughness. Lots of people have tried for a long time. The one thing that is changing now is the consistency and the frequency of data that allows a much better short-term variability. Because one of the key challenges that we have if you're trying to look at soil moisture, the biggest challenge is that often where the soil is moist is that vegetation, if it's not growing already, it will be very soon. So vegetation then causes an obstruction, or it obstructs your view of the surface, because you've got to get through the vegetation first. And the other thing that changes with soil is that when soil gets wetter or drier, typically depending on what type of soil it is, there may be changes in the surface roughness. Add into that changes that farmers might do in terms of agricultural fields that change the surface roughness, and you potentially make it much more complicated. But it's much more opportunity now that we have much more frequent data. The other thing just to stress here is that it's all about liquid water content. As soon as water forms into ice crystals, the microwaves don't interact with them. And you can do that experiment at home. I don't suggest you put a just an ice cube into your microwave oven, but you can put an ice cube in a cup of water, not glass, cup of water, and you'll find that the water is boiling away before the ice cube has done anything. And that's because the liquid water molecules are absorbing the microwaves in the microwave oven, and they're getting all energized and it goes up. In the ice cube, the microwaves just go straight through it. And that's the science behind why you don't try to cook a frozen chicken in your microwave oven, because essentially you can end up with a very crispy, almost burnt to a crisp outer skin of the chicken, while the inside is still frozen. And so it's because those frozen water molecules just don't absorb the microwaves. In the context for us, that's important because as soon as the ground freezes, the dielectric constant drops and the backscatter drops significantly. It's also the case with vegetation. So if vegetation freezes, and I believe I've heard tell of trees in the Arctic, for example, in sort of northern Canada, where they've evolved to allow it to freeze essentially. But once it freezes, it becomes completely transparent to the microwaves. So you have to take that into account when you're interpreting your data, is that what's the temperature. And certainly we're not going to get many frozen trees, but you'll certainly get frozen ground surface. And the change from a frozen ground surface to a thawed ground surface is such a dramatic shift in the radar cross section that you have to be aware of that impact. The last thing I want to measure, and there was at least one person that said that they had, I think there was two people that said they had polarized sunglasses. But one of the key things about the way that when the wave interacts with a surface is that if you have a surface and you have a horizontal wave that arrives, it's going to oscillate those electrons on the surface much easier than a vertically polarized wave. When they both come in at 90 degrees, it doesn't matter which polarization it is. But when they come in at an angle, it does make an impact. So as these waves come in and interact, some waves get absorbed, some get scattered. But in terms of the reflectivity, so quickly to explain what this diagram is showing you. This is our incidence angle. The reflection coefficient and the reflectivity are related because the reflectivity is just the square of reflection coefficient. So both of these diagrams are showing you the same thing. And you'll notice that for each measurement, it's done as an HH or a VV. So the reflectivity actually increases as you go to increasing incidence angles. And that's a weird thing in itself, okay? And I'm going to get you to do a little experiment in a second. But the VV component drops to a minimum and then increases up until it reaches a maximum again at 90 degrees. So a quick test for you all. Does anybody want to anybody know what that angle is called? This angle where the reflectivity drops to a minimum in the vertical polarization. Anybody know it? No. Can we say the critical angle? I don't know it as that. I know it as the Brewster angle. Named after David Brewster. He was a physicist at St Andrews University around about the turn of the 18th to 19th century. Also invented the kaleidoscope. But that's that low point there in the vertical polarization. That is why your Polaroid sunglasses are very effective, because if you've got polarized sunglasses, okay, so these aren't polarized sunglasses, but they would do the equivalent of polarized sunglasses, is that at an angle of roughly about 60 degrees incidence angle, there is almost, the reflectivity of the vertically polarized waves is almost zero, but the reflectivity of the horizontal waves is very high. So if you are looking at, for example, a water surface, a wet road surface, a snowy surface if you're a skier, water surface if you're into water sports or you're into fishing, the wet road surface. So these are all the things that Polaroid sunglasses are ideal for. Is that what the Polaroid sunglasses do is that they only allow through the vertically polarized waves. So at roughly that incidence angle where you're getting the glare off that shiny surface, you only get the horizontal waves that are scattered. If your sunglasses get rid of all the horizontal component, then the glare, the strong reflective glare off the surface, that gets cut out completely. And that's where if any of you do have a pair of Polaroid sunglasses in the house, you can go and experiment with that, and you'll see that anything that is reflective, pair of glasses, screens for computers, all of these things, is that they will be scattering. Not if you look at it straight on, because then you're down at 0 degrees incidence angle. But if you're looking at it at an angle with an incidence angle about 60 degrees, you will notice that it completely gets rid of the reflection. And so I tell you about this just to emphasize why the polarization that we measure is telling us something about the surface. In this case, it's potentially telling us something about the orientation of the surface. Now I'm just going to take 2 minutes to fill up my glass of water, and I'm going to ask you to do something for me as an experiment in those 2 minutes. So basically what I want you to do is get a flat piece of paper. It could be an envelope like I had, a flat piece of white paper, and something that is very solid. So something that has got a nice flat solid surface. So a hardback book is a good example. It could be a tray from the kitchen. It could be a book from your shelf. It could be like an iPad or something. So something that's just really flat and a piece of paper. Okay, if you want to go and collect that now, you get to do the home experiments. And I'm just going to go and fill up my water glass. Hold on. Okay, is everybody back? So from this diagram, one of the unusual things that appears is that the reflectivity goes up to 1. So 100% reflectivity when you get to 90 degrees incidence angle. I like to do this experiment just because it's quite unusual, and it helps to emphasize why the interaction of electromagnetic radiation with surfaces is not always what you expect. Because what that would imply is that any surface, if every surface has a shape that it's not all exactly the same, and so the Brewster angle, for example, can shift a few degrees in either direction. But if you're looking at 90 degrees, so that's essentially 90 degrees incidence angle is looking along the edge of the surface. That would imply that it gets to 100% reflectivity, even though it's only, this surface is down less than 0.1. So less than 10% reflectivity when you look at it normally, flat on. And what I need you to do, if you're all doing this at home, is to look at as close to 90 degrees as you possibly can, and then get close to, say, a light surface. So if you've got a light on the ceiling, not a light surface, a light on the ceiling, or it can also work if you look at a window or if you've got a bright window. But you will see, if you look just along at the grazing angle, you'll see that even a flat matte piece of paper is reflects the light. So you can see a reflection of the light on the paper just as you look along it. Do give me a thumbs up if you can actually see that. It's much easier to do when you're actually in a classroom and you can make sure that everybody can see it. No thumbs up. Does that mean nobody saw it or nobody tried to see it? Oh, no, there is some thumbs up. Excellent. Thank you. Right, just a couple of examples of what it means when you get the polarization. So Crispin gave a fantastic example in his context of looking at the multiple polarizations. You can combine them in different ways. You can create nice, pretty pictures. So even just with the VV and HV, you can see that there are areas that are lighter and whiter and areas that are redder in this particular image. And this data, this is fully polarimetric data. So this has got, unlike you'll get access to, so Sentinel-1 gives you 1 transmit and 2 receive polarizations. But if you can transmit both vertical and horizontal and receive vertical and horizontal, then you get much more rich information about the surface. It tends to be only experimental modes that do fully polarimetric data in space, but it does add extra information in terms of what you're getting about the surface in terms of the orientation and shape and size of scatterers. Oh, and a few people said, yep. And Stuart says, actually seems more reflective the shallower the angle. Yeah, so if you can get it right on the grazing angle, it's not quite a mirror, but considering it's only a piece of paper, it is remarkably reflective. And a particularly good example is a window. If you've got astragals, so if you've got the little bars across the window, is that you will actually see the reflection of the bars. It's not just an added glow of the light that actually is giving you a reflection. Okay, so here's one of my this is one of my favorite topics, and I've created some new animations for you because it's quite interesting how corner reflectors, both how they work but also how they turn up in nature. And corner reflectors are essentially a consequence of two planes, so that you've got a scatterer that is in hang on, I'm just adjusting it. So you've got a scatterer that's maybe in the vertical and one in the horizontal, or you might have multiple panels together that are that make a corner. So I'm going to explain a little bit more about that. And then the other special scatterer is the Bragg scattering, which I'll show you some nice examples of. So again, just using this as my starting point, the key thing is that, well, what happens down here and how much of the energy is directed back to the sensor. Now, there's two things going on here. One is that a target that scatters a lot of energy directly back is going to look much brighter. But also just take into account the range bin. If all the energy from us comes back in that same range bin, it means you'll get a really bright signal, because all the energy is coming back just at the same. If it comes back at the same time, it will look really bright. It has to go into 1 pixel. So bear that in mind as well. And the first corner reflector is it's what's called the dihedral corner reflector. So it's just 2 planes. They're at right angles to each other. Sorry, I'm just trying to draw that here. So there's that plane and that plane are at rolls. And I'm going to show you some animations that will convince you of the geometry of this. That means that it doesn't matter which direction the signal comes in, it will bounce off one plane, then off the other plane, and come back in exactly the parallel direction to the way it came in. And I've got an animation that's going to explain that. But that idea of the right angle is quite significant. And it also occurs when you've got a cylinder. So the key thing about having a plane, so if you've got 2 planes at right angles like that, it only works if you come in, if your signal comes in at right angles to the axis of the corner. So it's got to come in and out that way. If you've got a cylinder, then you end up with this right angle. It doesn't matter if you come in from this direction or from this direction or from the front. It's going to hit the cylinder, the ground surface, and it's going to come back. And this actually occurs in this kind of shape, often occurs in a natural context, which is when you have vertical trees and horizontal water surface. So if you've got a flooded forest, you might expect to get a very bright signal because you get this double bounce effect of hitting the water, hitting the tree, coming back, or hitting the tree first, hitting the water, coming back. And it's because of this right angle. And here's actually another example of these really bright targets here, and it's been scaled so that you can see just how bright these targets are. Actually correspond to these big oil drums in, I think it's St. Lucia, this image. So these are acting a bit like top hat scatterers, and that they're big cylinders surrounded by a horizontal ground surface. So it doesn't matter which way the sensor is looking at this, it's going to get a strong return from the ground surface hitting the vertical side of these cylinders. The next important one is the trihedral. So in this case, when you've got 3 planes, this is equivalent to the corner of a, it's the corner of a cube. Okay, so it's a bit like that. So we've got our 2 planes here at right angles. And put it on another surface. We've got 3 planes all at right angles to each other. And the reason that's important, so this corner of a cube, is that it much like the top hat scatter, is it doesn't matter which direction it comes in, because if it comes in any direction and hits one plane, then another plane, and then out again, it always comes back out exactly the same direction it went in because of these 90-degree angles. Now, these kind of corner reflectors are used as calibration targets when they're calibrating spaceborne radar. They're also used as key points to determine geographic correction. They're also very useful in terms of building into infrastructure projects, because then the radar system can actually pick up the signal. So I showed you that map of the small changes in the surfaces in London, is that if you actually build in a corner reflector into your bridge or your building, you will be guaranteed to get a very strong signal that you can measure from spaceborne radar and then monitor the infrastructure movement over time. But it also occurs naturally. Well, not naturally. It occurs by chance in the way that structures are built, because you build structures and typically you will end up with vertical walls and horizontal panels, and the ships that we'll see turn up as very bright targets in the ocean. That's partly a consequence of having lots of these corner reflectors just by chance. You also sometimes do it more than just by chance. So here's an example of having a corner reflector which is used to make a little boat look like a very bright target in the big ship's radar systems. So you'll get a trihedral corner reflector, you'll get a strong return, and the big ships will, even though the ship itself might not have a strong radar scattering signal, this corner reflector will generate a very large return signal. And this is part of the reason. So this is a TerraSAR X image of Las Vegas. And you'll see that there are lots of bright targets here. It looks like they've put all the lights on in Las Vegas, but that's what you're seeing, is that these corner reflectors that are a consequence of just the construction of these hotels. I presume most of them are hotels with casinos at the bottom. And what you're doing is picking out these points where there are little corner reflectors which are scattering significantly back to the system, the radar system. So here's another TerraSAR X image. This is Gibraltar, and we've got some ships now. So these ships definitely look quite bright on the water surface. All of these bright points, and you'll notice that they're a bit more regular compared to the sargassum. The sargassum blobs were a bit more blob-like, whereas these look in a more regular fashion. And if we zoom in, we can see that they're made up of quite a handful of pixels here, giving you a bright target compared to the contrast of the dark water, because of all the contours and the metal structures that are on these ships. The other thing to note here, which I will come back to on Monday's talk, is the fact that where the wake of these ships appears in the image. So this here is the ship's wake, but the ship is here. So there's a displacement between the location of the ship in the image and the location of the wake. And that's significant because when we look at Monday somebody asked this week about what is it that makes the aperture synthesized. So what is the aperture in the synthetic aperture radar? Is that on Monday we'll have a quick look at that to see that there is an element of the processing that assumes that everything on the surface has stayed the same. If you remember, the answer I gave when you asked on Monday about that was that I can use a small antenna. If this is the size of my small antenna, I can move my antenna, collect data every point along that journey. As long as I collect all the data, I can combine it together to synthesize a really long antenna. But that's making an assumption that everything I'm looking at on the surface has stayed exactly the same while I collect all that data. If you've got a ship moving on the surface, and indeed anything moving on the surface, your assumption about a static scene no longer applies. And the result of that is that anything that is moving in your image gets relocated in your image to the wrong place. We'll touch on that again on Monday. But that's why you get this displacement. Now, what's interesting about that is that it's in proportion to the velocity of the object that you're imaging here. So you can actually make an estimate of how fast this ship is moving by looking at the displacement from the wake compared to where the ship location is. The faster it moves, the greater the displacement. Here's a little animation to illustrate the corner reflector effect. So this is just to show you how it doesn't matter which, these are right angle on the right angle corner reflector. And these orange pulses that are coming in, it doesn't matter which direction they come in, they always go back in the way that parallel to the direction that they came in at. So that's significant. That's definitely going to give us very large backscatter whenever we have a corner reflector. But it's more than that. It's not just because all the energy is being scattered back in the direction of the sensor. It's also because the geometry of the corner means that all the energy arrives back at the same time. So you'll see that these pulses, they all leave at the same time. They hit the corner, and then they all arrive back at the same time. And the reason for that is because this distance here that it travels between the horizontal and the vertical, that's the extra distance it's traveling compared to the, if you compare it to the distance of the pulse right down the middle, it's extra distance. It goes from into the corner and back again. And the geometry of the corner is such that this distance here is always half of that distance there. So they all travel the same distance. So all of these pulses arrive back at exactly the same time. And that applies, it doesn't matter what direction it's coming in, it doesn't matter how large this corner reflector is. So the signal can come in over here, it can travel all the way back there. Even if it takes that path, it will arrive back at the same time. So not only is all the energy coming back from a corner reflector, but it will all end up in the same, all that energy will end up in the same pixel. So if that's a tall building and a flat water surface, is that all of the energy will come back to the sensor because it's a corner reflector, but all at the same time, and therefore all gets put into the same pixel. So it's a huge jump in terms of the signal. And that's one of the reasons that we end up scaling our radar data in decibels, is because we actually end up with signals that are really, really high, extremely high. And the other thing to note is that the location where it appears to be in the image, in terms of the image location, all of the backscattered returns appears to be at the apex of the join. So where the vertical and the horizontal meet, just in the corner there, that's the location that the radar image will put all of these signals. Somebody's just asked a question. Let me just check that. Jonathan's asking, does water need to reach a minimum depth before acting like this relative to the SAR wavelength maybe, or just deep enough to cover the surface and any roughness? Exactly. So the liquid water forms quite a very strict boundary in terms of the medium that it's interacting with. So if you have a rough surface and you cover it with water just so that the water is just covering all the surface, it doesn't matter how thick the water is, that will provide that will make it smooth. It will look smooth. Right, like I'm going to cover today is what's called scattering. It particularly occurs from periodic surfaces. Okay, so that can be over water surfaces. So when you've got wind blowing just in the right direction, you can get higher or lower. These are actual tropical rain cells that are disturbing the water surface. But just to remind you, what we're on a scale of our wavelengths are certainly for Sentinel, it's on this kind of scale, a few centimeters. So roughness on that kind of scale is going to have an impact on our scattering. And I'm not sure how well this comes across over Zoom, but this is a short video of just me near where I live, of the water. And you can see the wind blowing across the water, creating these little ripples. And these little ripples are on a scale of centimeters. And it's actually these centimeter scale ripples that impacts on the backscatter from a water surface. And Crispin mentioned how on water surfaces, if it gets too windy, you end up with the surface getting rougher, and so the signal can actually look brighter. And the reason that you get this, there's a two-scale model that you can use to explain what happens over water surfaces. In large water surfaces, so when you're out into the oceans, you have your large gravity waves. And then on top of that, you have the small capillary waves that are caused by the wind blowing on the surface. And I've just, Paul is just noting to me that there was a question about biomass. I'll come back to that in a second. I'll finish the Bragg scattering first. And as I mentioned before, the key thing is that in terms of the geometry, if the geometry is just right, that this extra distance here, change the color, this extra distance here called lambda r, if that's just right so that it's half a wavelength, so that as it goes and comes back, the two wavelengths, the two waves coming back add together, so they become in phase. So it's just the right geometry that all the waves are coming back in phase. Is that if that geometry is correct, it's not just those two water waves there, it's all of them, and potentially all of them across a very large area, your whole pixel size. And what that can do is the waves all add together constructively and create a very, very huge signal, as long as you're looking at it just at the right incidence angle and the waves are just the right size. So it becomes very sensitive to the size of these waves, and you can actually use that knowledge and that relationship to determine the speed and direction of waves over the ocean surface. But it's also the case that you get regular surfaces in other places. So one that I've definitely seen is corrugated iron on a roof can create a very large backscatter. It's also metal, so it scatters really well. But another one that you can you can get Bragg scattering from is the wind ripples over sand dunes, because these form a nice regular surface. And what's very remarkable about this is that the sand is very dry. So the signal, the raw signal that is scattering from the sand surface is really low. But because of this constructive interference effect, where if all of these waves add together constructively, it makes such a huge difference in terms of the signal, is that even over sand dunes, so this is some sand dunes in the Western Sahara, is that if you look at the radar data, you can see you end up with these really, really bright. They look bright because they're, they look like little stars. I mean, because they're so bright, they're actually bleeding into the pixels next to them. You're actually starting to see the impulse response function of the instrument, that they're so bright. And this is directly a consequence of your Bragg scattering, so that these wind ripples are just at the right size that they're contributing a significant backscatter. In between these particular areas, the wind ripples themselves are probably the same size, but your incidence angle is changing as you go up and down the slopes of the dunes. And so it's only in one particular incidence angle, at one particular perspective, is that you get this constructive interference and what looks like really bright targets. Right, that's where I'm going to leave it today. So I'm going to pick up on the geometric distortion and the impact from vegetation on Monday. And we'll also use the look at the geometric distortion to help us understand a little bit about where this aperture synthesis comes from. What is the aperture? What is it we're actually synthesizing? Why do we do it that way? So we'll touch on that. We'll look at geometric distortion in SAR. We'll also look at vegetation and forestry in particular, because that's quite a long subject, so I wouldn't want to start that now and not finish it.